Thanks, Paul. Thanks a lot to the organizers for inviting me. It was really a pleasure to come here and talk to everybody the last day. I'm looking forward to talking some more. So my name is Daniel Wines, and I'm a postdoc at NIST, the National Institute of Standards and Technology in Gaithersburg, Maryland. Today, I'll be talking about accurate electronic and magnetic properties of 2D materials using QMC methods. So I'd like to acknowledge a lot of people that have helped me with this work throughout the year. So I'm going to talk kind of similarly to Fernando yesterday, give a very broad overview of a lot of different topics throughout the last couple of years. And if anybody wants to talk about some more details, happy to discuss a little bit later, but I want to give a broad overview about some of the work we've been doing with 2D materials during my doctorate. So my advisor, John Adja, is sitting right there. We worked a lot in 2D materials with Kyan Saritas and in collaboration also with Jaren and Juha from Oak Ridge. I'd like to acknowledge some of my other group members as well from UMBC, and also my group members at NIST, who have been very supportive of using this methodology in their workflows as well as part of the Jarvis project for materials design. So like Kamal Chowdhury and Francesca Tavazza as well. So I figured it would be fitting to have a nice QMCPACK logo on the first slide to show my appreciation for the code. So I'm going to give a little bit of an overview of 2D materials, talk about some of the limitations of using density functional theory for 2D materials, give a little bit of background, and talk about some of the applications we use QMC for 2D systems, specifically for gallium selenide, gallium sulfur selenide alloys, and magnetic properties of two-dimensional systems like chromium triiodide, chromium tribromide, manganese dioxide. And I'll talk briefly about some current work about 2D vanadium diselenide, but this will be covered more in detail by John tomorrow morning. And I'll also talk a little bit about some of the work going on at NIST as part of the Jarvis project, specifically our benchmarking effort of the Jarvis leaderboard, and some conclusions and perspectives. So I don't think 2D materials need much of an introduction. They've been a very hot field for the last 15 or so years. They're the next logical step for smaller electronics, so smaller transistors, LEDs, flexible electronics. There's also very interesting properties different than the bulk that make them suitable for things like 2D magnetic devices, spintronics, hydrogen production, energy storage, and there's several more applications as well. So the rising stars, and I guess not really rising anymore because this is now a field that's been going on for over a decade very actively. So there's mono-elemental materials like graphene, phosphorine, and so on, transition metal dichalcogenides such as molybdenum disulfide, tungsten diselenide. We have post-transition metal chalcogenides such as indium selenide, gallium selenide, transition metal halide-based materials, such as the 2D magnets like chromium triiodide, nickel diiodide. We have transition metal oxide monolayer materials and MXenes as well. So why are 2D materials difficult to model? So I come from a DFT background and I transitioned into QMC a couple of years ago. So some of the difficulties with modeling these 2D systems, and I'm calling them 2D, but I really mean kind of quasi 2D. So low dimensional, few layer, quasi 2D systems they have very strong van der Waals interactions, strong interlayer interactions. Many of these materials are transitional metal based. So they have oftentimes correlated electronic structure. There's reduced straining. So there's strong excitonic effects, which cannot be captured with DFT. And a lot of systems have very strong spin orbit coupling, which result in things like splitting of the bands and also topological properties as well. So just as I said, DFT has been very successful for a very wide variety of systems, and there's very well documented and characterized DFT codes. We have a good balance between computational efficiency and accuracy. But some of the shortcomings for certain systems are, of course, that the results depend on the exchange correlation approximation. Van der Waals interactions require certain corrections, or van der Waals functionals. Systems with strongly localized electrons, they require corrections like DFT plus U. and band gaps are underestimated. So some of the proposed solutions are to use post-DFT methods like many-body perturbation theory or stochastic methods like quantum Monte Carlo. So I don't think quantum Monte Carlo needs much of an introduction, but I'll talk about the specific forms of QMC that we were using. So we are using a combination of DFT, variational Monte Carlo, and diffusion Monte Carlo to study two-dimensional crystals. So although it's more computationally intensive, a lot of simulations are needed to achieve our answer. The scaling is pretty nice with the system size, thanks to the current state-of-the-art software, QMCPACK, and all of the developers and their assistants as well. So when I say DFT, I mean specifically plane wave DFT. You get the wave function using quantum espresso with the newly developed pseudo potentials. So like I said, in diffusion Monte Carlo, we're simulating the diffusion of walkers in imaginary time until steady state is reached, and we have controllable approximations like time steps, finite size errors, and also we optimize our nodal surface with methods such as the ones Fernando was saying yesterday by tuning the Hubbard correction for certain systems. So I added this slide yesterday because there was a lot of talk about running QMCPACK on different machines. And I just want to emphasize that UMBC is a relatively small university, and we didn't have access to these gigantic computers that we saw over there. And it's a lot of hope for QMCPACK can be run very nicely on small machines. So this is a picture of me from early 2019, before I did a single QMC calculation, where we had a tiny cluster that we bought for the group. And we ran all of the QMC on there for these projects. So the code is very well suited for architectures like this. And again, a very promising route for other people at their universities and departments. So before I get into some of the work that we did, I want to acknowledge a lot of the awesome work that people have done for the last 8 or 9 years in the field of two-dimensional materials with quantum Monte Carlo. And it's been very exciting to see this field grow and be in it as it's growing. So as you can see, there's been a lot of developments in the methodologies, a lot of developments in the pseudo potentials, and just the capabilities of what quantities you can get with QMCPACK. And I just want to acknowledge this first really great paper from Luke Schollenberger and David Tomanak about the properties of bilayer phosphorine. And then we've really moved to getting more complicated properties and more complicated systems, such as Lubos Smita's work on getting the band gap of phosphorine. And then also things like getting the geometry optimization using the surrogate line search method, which Darren's going to talk about. So doing this for systems like chromium triiodide and doing this for systems like germanium selenide. So when there's a very strong coupling of structural properties or electronic embedding, really being able to resolve these differences at the DMC level has been very cool. And also looking at more involved systems such as either molecular or atom absorption on top of monolayers. So really being able to extend this method to realistic materials in the 2D regime. So I want to talk about a couple works that we did. So starting with one from a couple years ago regarding two-dimensional gallium selenide. So gallium selenide is a semiconductor. It's suitable for applications in photovoltaics, for transistors, water splitting. Atoms bind very strongly to the surface. So there's a lot of energy application. So it's a post-transition metal chalcogenide material, and it's predicted to have a lower exciton binding energy than traditional TMDs that might have an exciton binding of hundreds of MeV. So we chose the system because it was very reliably synthesized and very promising for future technologies. And our motivation to look at this through a many-body lens was that DFT functionals disagree and are off from experimental values. Sorry. So I want to talk briefly about experiments on gallium selenide. So it's been shown to have a lattice constant of 3.74. The quasi-particle band gap has been measured to be 3.5 eV on a graphene substrate. optical gap has been measured to be 3.3 on a silicon substrate. And also alloys have been synthesized in fuel layer form. So it's demonstrated that the band gap is extremely tunable. So our goal was we wanted to obtain chemically accurate results for gallium selenide using DMC, calculate the lattice parameters, calculate the band gap, and also benchmark heavily with DFT and GW results against experiment. So the first thing we did was we wanted to obtain the optimal lattice constant and sort of demonstrate the power of DMC here, where what we did was we took, as you can see here, with different functionals, we have a pretty large spread in what the lattice constant is with respect to experiment. So what we did was we actually created the trial wave function using different density functionals and then isotropically scaled the lattice to find the lowest energy. And whether or not the wave function was created with PB, LDA, or SCAN, we actually find the same answer in near perfect agreement with experiment. So this was step 0 of what we did. More interestingly, we wanted to focus on the electronic structure of this material. And the motivation for this comes from there's a very small energy difference between all of the high symmetry points at the conduction band edge. So as you can see here, depending on which DFT method is used or which pseudopotential is used, it results in, of course, at the DFT level, it's an underestimated band gap. And then there's a discrepancy on whether the material is direct or indirect, depending on which methodology is used. So in addition to the DFT dependence on these kind of factors, GW is also very dependent on the starting functional to get the initial wave function for the perturbation. So alongside of our DMC excitation energies, we benchmarked this pretty heavily with other methods. And as you can see here, there's a lot of varying direct or indirect discrepancies. And we confirmed with DMC that 2D gallium selenide is an indirect material and the quasi-particle gap is in very good agreement with the experiment. And from calculating the optical gap, we found that the upper bound on the X time binding energy, so the maximum value that it can be from the differences is 80 MeV. So by doing this, we have a very in-depth theoretical benchmark for this material that can hopefully be applied to other 2D semiconductors as well. So we wanted to take this a step further and try to look at alloys with QMC. So alloying is a very effective way to tune the properties of 2D materials. So like I was saying on the previous slides, at the fuel layer limit, gallium sulfur selenide alloys have been investigated, and also Janus materials where one side would be sulfur, one side would be selenium. So sort of analogous to the Greek god here. These have also been studied at the DFT level as well. So traditionally, when studying these kinds of systems, DFT is used in conjunction with a method like cluster expansion, using codes like ADAT and your favorite DFT software. But what we really wanted to do was we wanted to develop a procedure to study these 2G alloys with a similar atomic environment. So within this chemical space, using DMC in the workflow. So what we did was we tried to study effects of different Jastrow parameters on the VMC and DMC energies to see if we could share Jastros between these materials and minimize the number of VMC simulations that are needed for all of the calculations. So as you can see here, here's the DFT energy hole diagram, where this is the alloy formation energy calculated by this formula here, which is dependent on the endpoints and also the concentration of sulfur. And we selected certain points from this diagram to compute with DMC. So it's circled here and shown here. So to do this, what we would have to do traditionally is do a DFT calculation, optimize the Jastrow for each individual alloy, do the DMC, and then, of course, our time step and finite size convergence and so on. So what we really wanted to do was try to modify step 2 to save the costs. And we proposed that it would be convenient if we could take the Jastrow parameters of the structure with the smallest Wigner site cell, with the smallest Wigner sites radius, and then use those Jastrow parameters for the other structures within the same chemical space. And we wanted to test the validity of this and how sensitive this might be, where we could maybe propose this for more complicated systems and then minimize our VMC costs. So here's kind of just a difference between VMC with the self Jastros and the shared Jastros. And we find that sharing Jastros between materials in this chemical system for gallium sulfur selenide is nearly identical at the DMC level. And the error is still decreased no matter which Jastros are used. So it would be most convenient to use the Jastros from the cell with the smallest WS radius, which was from here, and then perform the desired calculations that way. So here's sort of our quasi DMC calculated energy hall diagram, where we have comparisons of DMC energies calculated with the self Jastros versus the ones from the smallest Wigner site cell. We see that they're nearly identical. And we chose this system because DFT and DMC are in very close agreement. So it's beneficial that we can benchmark structures that have low formation energy and high formation energy as well, and hopefully extend this idea to other systems. So here's sort of how the workflow is set up, where we have an initial lattice. We randomly create different structures with the SQS method, get the DFT whole diagram. We find structures that we like to study further, find the structure that has the smallest Wigner sites radius, optimize those Jastros, reuse those Jastros, and then perform DMC to get those formation energies. So we did sort of a cost analysis of this, and we found that when the self Jastros are used, the VMC accounts for a substantial amount of the computation time to optimize those parameters. So about 1/4, which is pretty significant if you wanted to scale this up for maybe instead of picking 4 or 5 points, doing this for hundreds of points. And it does not change the DMC time needed to achieve the target error bar. So I'm going to shift gears a little bit here and talk about some more recent work about 2D magnetic systems. So 2D magnets have been a very hot field for the last couple of years, especially with the measurement of a 45 Kelvin Curie temperature from chromium triiodide in 2017 in Nature. So 2D magnets are a very important class of materials for spintronic devices and information storage. And they're often correlated systems that are difficult to accurately model, and they require things like the U correction. So these calculations can be revisited with accurate many-body techniques. So here's just an example of some of the predicted 2D magnets here. So magnetic materials have been very popular for QMC. And I want to acknowledge some really great work from the last couple of years, especially the one from Daniel Staros and Brenda Rubenstein and Jaron and everybody, where they optimized the geometry of chromium triiodide with the surrogate Hessian method and also DMC, along with some other really nice work from Fernando and throughout the years with this as well. So we can study these materials with QMC and find very interesting properties such as magnetic moments, Curie temperature, magnetic exchange, and also things like interlayer binding energy, structural parameters, and so on. So from ab initio calculations, it's very common to sort of map our ab initio energies to a 2D model spin Hamiltonian. So in this case, we can construct a Hamiltonian that has terms for things such as isotropic Heisenberg exchange, easy axis single ion anisotropy, and anisotropic symmetric exchange. So from our energy-based calculations, we can determine these values, and we could use those values for things such as performing classical Monte Carlo simulations, or we can plug them into analytical models to estimate values like transition temperatures. Again, this Hamiltonian can have more involved terms, so it could have interactions like DM interactions or Kitaev interactions, but for our cases, we just stuck to this more simple Hamiltonian for these magnets. So at NIST, we've been focusing a lot on incorporating accurate methodologies into our workflows as part of the Jarvis project, which I'll talk a little bit about at the end. But what we wanted to do was combine methods like DFT plus U and QMC to accurately characterize 2D magnets. So we published this paper earlier this year where we sort of took a case study of 2D correlated magnets with chromium X3 stoichiometry, so like chromium triiodide, chromium tribromide, and we added this to the workflow. So here's the Hamiltonian I was showing before. And again, the strong motivation to work on problems like this comes from the strong variability in the DFT results for things like magnetic exchange or anisotropy and so on. So it's important to note that before this, there's a method by Torelli and Olsen from Denmark from a couple of years ago where they actually derived the model to get the TC of magnetic structures with out-of-plane anisotropy based on these parameters that can be calculated with DFT or other ab initio methods. So what we proposed to do was similar to what Fernando was saying yesterday. We can take our structure and then optimize the value of U, so get an optimized nodal surface and find the U that gives us the lowest energy. And then from that U, what we can do is we can compute energies for different magnetic orientations to get values like magnetic exchange. And then when we were doing this project, spin orbit was relatively new in DMC, so we didn't get the chance to work on that. But what we can do is we could take that U value and then perform more involved calculations for spin orbit energies to get things like the magnetic anisotropy and plug these into either a model or a classical Monte Carlo method to get the Curie temperature. So just demonstrating what we did here is where we tuned our nodal surface, optimized U to get what got the lowest energy, and then use that U for subsequent calculations where we found statistical bound on magnetic exchange and Curie temperature in very nice agreement with the experiments with less of a dependence on the value of U and the functional. And the same workflow can be applied to other magnets as well, with our goal of sort of increasing the number of materials we can add to our data set here at NIST. So here's kind of just if anybody wants more details about this, we very exhaustively benchmark these materials here in JPCC, where we use different functionals for anisotropy, different functionals for J, along with QMC, and we have very rigid tests of different geometries and so on. So very interesting. And from this, we could also do things like we can get estimate the spin density using the QDens tool in QMCPACK, and also integrate to find the magnetic moments as well. So I went a little bit out of order. So that was a recent paper we did, but we also had the same workflow developed for manganese dioxide while I was at UMBC in collaboration with John and Kyan Saritas. So on a similar wavelength, 2D manganese dioxide is another 2D magnetic material that's been reliably synthesized. This one is a semiconductor predicted to be ferromagnetic at the PBE level. And actually, John predicted this material in his PhD thesis over 12 years ago. So it was very fun to revisit this through the lens of QMC. So by looking at the DFT benchmarking, we find that there's very significant discrepancies in the favorability of the ferromagnetic or the antiferromagnetic orientations. So depending on which functional is used and which U value is applied, favorability is very different. And also the exchange energy varies from, let's say, -55 to +18 MeV, which is very significant for looking at magnetic properties. So we applied the same workflow and we optimized our nodal surface by changing the value of U. We found 2.5 EV was the fitted U value. And then we went on, calculated J with QMC for different magnetic orientations, and then found the anisotropy parameters from that optimal U that we found, where we confirmed that manganese dioxide in freestanding form is a ferromagnet with out-of-plane anisotropy, and the upper bound on the TC is 28.8 Kelvin, which is less than chromium triiodide. So one interesting thing that we looked at was, again, the spin density using the QDens tool. And we found that actually on the oxygen atoms, the spin density is polarized anti-parallel with respect to manganese. And this is an effect that is only captured in DMC and also DFT plus U. So without the U correction, this is not captured at all. So some really nice work that we did recently, earlier this year with, in collaboration with Oak Ridge people like Juha, Kyan, and Jaren, where we looked at the properties of two-dimensional vanadium diselenide. So vanadium diselenide is a two-dimensional system that's been controversially predicted to be a room temperature ferromagnet on top of a substrate. And we noticed that looking at the two different phases of vanadium diselenide, the structural parameters, the phase stability, and the magnetic properties are very intertwined. So what we ended up doing was we used structural optimization techniques with QMC methods, so that surrogate Hessian line search, which Jaren will talk about later, to find and resolve these discrepancies. And then some current work is focusing on the T phase, where we're looking at magnetic properties similar to the workflow that I previously showed. So this will be covered in detail tomorrow by John in the morning. So I want to shift gears a little bit and talk about some of the work going on at National Institute of Standards and Technology for my last, I guess, third of this talk, I'm part of the Jarvis project here, which is an open access set of tools and databases really geared toward materials design. So it can be found at the link here, jarvis.nist.gov. Registration is free. It just requires verification on our end. So it was a project established in 2017. And so far we have over 40 articles. There's over 20,000 users worldwide. And in our DFT database, we have 80,000 materials. So 80,000 materials may sound like a very small number, but it's actually what the intention of Jarvis is. So Jarvis is meant to focus on a smaller number of materials, but really try to expand on the number of properties, expand on the convergence of the density functional theory calculations, and expand on the accuracy as well. So this is a different goal than other databases such as the Materials Project. And if anybody saw the news recently, where Google, DeepMind, and Microsoft have had millions of DFT calculations just focused on the convex hull. So we want to go beyond the convex hull, look at properties such as topological properties, superconducting properties, phonons, elastic properties, thermoelectrics. So there's very property-focused studies all involved here for 2D materials and bulk materials. We do a substantial amount of outreach events too at Jarvis. So we have a Quantum Matters and Materials Science workshop held at NIST in the wintertime, which I'll talk about at the end a little bit. And we have an Artificial Intelligence for Material Science workshop over the summer. We also have Jarvis Schools, which are hands-on sessions where we travel to national labs or universities. We spend the whole day giving an overview of our tools, lectures, and we have a lot of hands-on Google Colab notebooks to teach students, to teach postdocs, or anybody interested in that. And the good part is people that want to host us don't have to pay for us because they're not allowed to do that. So they're all federally funded by us as well, if anybody is interested in setting up any events. So there's a new Jarvis review article out, which was featured in Applied Physics Reviews, where we just kind of detail some of these updates. So if anybody's interested in learning about this project some more, about the update to the number of materials, updates to the methodologies, and the different applications as well, along with the Jarvis Leaderboard project, which I'm going to talk about a little bit right now. So there's been a lot of talk in this session about benchmarking of methods. And at NIST, we're very focused on measurement science. And I think what people don't always consider is that calculations are measurements, and they should be precise, and we should have good benchmarks for not just one or two properties, but for a range of properties and a range of different fidelities. So some of the challenges in material science right now are reproducibility, transparency, validation of methods, the fidelity of the data, what should be considered data versus metadata, and really what is the ground truth that we need to compare our models to? Is it experiments? Is it higher accuracy electronic structure methods? How does this really change depending on what method we're using? Are we using an AI method and predicting DFT accuracy? or experimental accuracy? These are questions that we have to ask ourselves. So we really want synergy of computational and experimental databases. So my colleagues and I, one of these initiatives that we've been trying to do is the Jarvis Leaderboard, which can be found at the link here, which is a large-scale benchmarking effort across multiple different fields for multiple different types of materials and properties. So you can see our archive paper up here, where we kind of go into detail about this more. So the large-scale benchmark of materials design methods. So we have a lot of collaborations from government and academia involved in this. And although there have been other focused benchmarking efforts in the field, like such as MatBench or other platforms like that, there hasn't been a unified platform to do this. So we have different categories of benchmarks here for electronic structure, artificial intelligence, force fields and machine learning force fields, quantum computation algorithms, and an experimental component as well for different types of data. So like atomic structure data, properties such as the band gap or the bulk modulus, image data, different spectra that you can get from experiment or from density functional theory calculations. We also have components for text and also analytical models as well. So it could be sort of broken down here in a way where you see we have categories of electronic structure benchmarks, and this can be broken down into DFT, QMC, GW, type binding, all with different specifications like the codes that are used, the code versions, the functionals, so on. And a similar analogy for AI as well. So we have descriptor-based AI, graph-based, transformer-based, all with different specifications as well. So really, this is a very user-focused platform here, and it's in its infancy still. So what we've done is we've put specific benchmarks on the website, and we encourage people to upload their data and upload their models as well. So for example, here is just a very basic example that I had QMC in, where you can see here's a model for the bulk modulus of germanium, which has VASP by D 890, so bulk germanium. And here you can see that this is the MAE is calculated with respect to the experimental value. And there's different contributions here of different methods. So we have different DFT functionals and also DMC with respect to this as well. So in addition to just providing a file of value or maybe uploading your machine learning model that can do this, we require more information. So we have metadata associated with each submission that has things that can reference the data and also reproduce the data as well. So this really asks the question, why do our methods succeed or fail? And there's really no avenue to report if or where things went wrong. So these details are not reported in papers. And we really want to try to increase reproducibility and transparency. This is what John was talking about before of uploading people's workflows and scripts. So in the Jarvis leaderboard, if you want to contribute, we require metadata and a run file for each contribution. So we want a file in there where it doesn't have to exactly reproduce the file. I know this is difficult in QMC because there's a lot of steps to it, but we at least want the workflow or the procedure of how you got that number. And in the metadata, we want things like your team name, URL, a DOI associated with each quantity, so whichever paper that data came from, what software you were using, so were you using the batch code, were you using the legacy code, which hardware were you running on, the timing of it, the uncertainty, and just other specific calculation details such as choice of pseudopotential and so on. So in addition to, let's say, okay, I'm going to upload my data to this benchmark and see how it performs, you could also visualize how this works for multiple benchmarks. And you could look at the contributions and the error with respect to the benchmarks in tools like Google Colab notebooks, where you could assess the accuracy of different methods. And this allows us to sort of validate methods or identify areas where existing methods are not sufficient. So maybe this will motivate us to develop newer methods or use more accurate models. And it could also identify materials or material classes which require these higher fidelity methods as well. So like I said, this project is at its very early stages right now, and it really depends on people, their feedback and their input, where we could sort of scale this up and then maybe have more of these conversations later on when we have more data in there. So we can kind of think about what problems do we actually want to solve with higher accuracy methods like QMC. So I just want to conclude with a couple things, and thank you everybody for listening. So here are the papers associated with some of the things I discussed. And I just want to say that 2D materials are very oftentimes, they have a complicated electronic structure. They require higher accuracy methods, and DMC can be used to accurately predict these properties and combine with DFT plus U and other methods to extract useful measurable quantities. And I think the time is now that there's a community need to incorporate these high accuracy methods into traditional workflows and databases. I think we need to go beyond DFT as a precursor for a lot of things. So with that, I'd like to also advertise a couple of things. So I think I have a couple more minutes. John has funding and he's looking for PhD students and postdocs. He's a very wonderful guy, and I'm not just saying that. He wants somebody to work specifically on quantum Monte Carlo methods for 2D materials, right? Or other stuff. Open broadly. I want to advertise our workshop at NIST also. So we have a workshop based on emerging quantum materials. I know some people presented there last year, and some people here are presenting there this year. So we have about 28 invited speakers from experiment and theory. There's also a poster session if anybody is interested in attending and presenting. Here are the registration details. So it's a very wonderful opportunity to meet with people and network, talk about some of the issues in quantum materials. I was also asked to advertise some postdoctoral opportunities in our group as well. So we have NRC postdoc opportunities in very different areas like quantum materials, machine learning, materials design, open to US citizens. So basically in an NRC position like myself, you have to write proposal and get funded. And also we have positions for the CHIPS Act funding that we received for multi-scale modeling of semiconductor defects and interfaces as well. So people with expertise in electronic structure, type binding, ML, transport properties, and device modeling as well. So this is also open to US citizens for now. So with that, I'd be happy to take any questions, and thank you again for the invitation.
Thank you very much. So it's open for questions.
Thank you. That was a really great talk, and I'm especially impressed with the Jarvis leaderboard. So my question has more to do with the magnetic materials portion. So you mentioned finding the best nodal surface by optimizing the Hubbard U. So could you explain why it's necessary to find the one that minimizes the energy? Because it doesn't seem like there's anything variational going on there. So could you explain the logic behind that?
Yeah, I think so DMC is a variational method. So you're changing your nodal surface to project out the lowest energy. So when you find the lowest energy and what gives you the lowest energy, this is how you can, I guess, your truest ground state energy. Of course, if you use more involved methods, like you have multi-determinants, maybe you could find lower energy, but this is probably the least expensive way to optimize the nodal surface. No, I mean the QMC energy. Yeah. Sorry for the
other questions or anyone online? Okay.
Can you guys hear me?
Oh yeah, go ahead, Daniel.
Yeah, so I also had a quick question about the U, and this is maybe just more esoteric. I'm not sure what word to use, but there are some systems in which you get a U that's like 14, 15, 16 electron volts that gives you the minimum, when you ran this on these materials, I suppose you don't have to check for that just because of the kinds of materials that they are, but did you have like a particular U cutoff? It looks like from this plot that that was 4, but in the future, you'd have to consider things like that, which then feeds into the possibility to need like orbital optimization or that sort of thing. So I didn't know if you had any comments on that future consideration.
Yeah, I think you have to be careful with this too, where you can be anything pretty much. And if it gives you the correct answer, it might not necessarily be for the correct reason. And for these materials and these set of elements, this is sort of a typical value of U. They're used, as you can see, the energy is not changing that much here with regards to the DMC energy with changing the nodal surface. So I think a careful consideration needs to be done prior to like really scaling up your calculations. You have to do very heavy benchmarking at the DFT level with several U values that are sort of typical for the system, and then try to optimize the nodal surface and see if it physically makes sense, I guess. But I agree with you that, yeah, that using very high values of U like that, yielding the right result, this might not be for the correct reason, I think.
So I'm going to jump in with a question about the Jarvis effort and maybe what distinguishes it from some of the other, more well-known databases. And I was wondering, do you include non-ground state materials? So for example, metastable materials, conditions other than ambient, high temperature and pressure in there, for example, right? What is the focus?
Yes, we include metastable materials as well that are, I guess by metastable, do you mean like far from the convex hull?
It's your definition to make.
Yeah, so we have materials in there that have unstable phonons that have are far from the energy hull, but it's all documented in there. So you could look up a material or you use the API and it says, okay, this is unstable with some of our kind of post-processing scripts.
Thank you.
So I have a question about the Jarvis. So you have a slide about uploading our data there and you are asking tons of questions. So if it is going to take more than 5 minutes of my time, I'm pretty sure that I'm not going to upload. So how are you going to promote users?
Yeah,
I mean,
so
do you have some kind of tool to extract those data?
yeah, that's a very, very good question. And I didn't go into too much detail because I didn't have too much time, but on the website, there's very automated tools to do this. So we have notebooks and videos that can really just like give you very brief instructions how to do it. It takes almost 5 minutes to do it. I'd say if you have 5 minutes of time, you can do it. It's low barrier to do it, I would say.
Yeah, we have time, but the last question.
So I also had a question about your uploads. Like we have automated tools as well for our catalysis.hub.org to lower the upload barrier for the users. Let's say I discover something. So for example, we had discover new material, new kind of structure, and we upload it to materials project, but they actually keep it in the contrib website. So they actually it's not public available. So you don't get a credit for discovery. How quickly you can publish our block structures and give us a credit for the initial publication? Link it to the paper actually.
So I guess just to clarify, for the benchmarking platform, we are only focused on well-known problems for now. So we're not focusing on newly discovered materials. It's just values that have been known in experiment, have been verified, and then model performance on those, in addition to performance of AI models as well. So yeah, we haven't touched the new material discovery part of that yet. For the leaderboard, no, you can, but we want people to upload details and maybe like scripts to reproduce that calculation as best to their ability as possible.